Now that you've mastered molar ratios, we can move on to the remaining steps involved in solving a stoichiometry problem. I thought now would be a good time for me to go ahead and give you the definition of stoichiometry. As you can see up here, stoichiometry is defined as using a balancing chemical equation to calculate relative amounts of reactants and products in a reaction. It is known as the quantitative study of a chemical reaction. Quantitative means how much. If you recall our work previously with chemical equations, we predicted what was going to be formed. That would be a qualitative study. Quantitative means we're going to figure out how much of a product can be produced or how much is involved in a reaction using a balanced equation. I believe that we can solve any stoichiometry problem by using 5 easy steps. Now would be a good time for you to pause the video and copy these 5 steps down so you can refer to them as we go through this PowerPoint. Step 1 is write a complete balance equation. We need to know what the recipe is for the reaction that's about to take place. And we spoke of this previously. A chemical equation is a recipe. Everything's expressed in moles. I advise you to label what is given in the question and what is you're going to solve for. It helps with the organizational skills as you work your way through the problem. The next step in a stoichiometry problem is to convert the given to moles. As we spoke about earlier, all chemical recipes are recipes with the coefficients representing reactants and products in terms of moles. Step 4 is what we worked on earlier this week, and that's the molar ratio portion, where you're going to set up a ratio between what you're given and what you're solving for. And you should have mastered that on the quizzes activity that we did. And the final step in a stoichiometry problem is convert moles to desired units. And for the next week or so, it's going to be grams. So if you look at this, as I summarized here down below, we've already covered step 4, molar ratios, in our work previously this week. We're simply going to add 2 more steps, one before the molar ratios, step 3, which is going to be converting grams to moles, and one step after the molar ratios, which is going to be converting moles to grams. We covered mole conversions earlier in the year, so in essence, we are really adding nothing new. We are simply learning how all the pieces come together in one problem, hence stoichiometry. Let's go ahead and try an example together. Here's the problem. How many grams of water can be produced when 25.36 grams of oxygen are reacted with an excess of hydrogen? So as we stated previously, step 1 is to write a complete balance equation. We actually used this equation previously in the molar ratio section. I personally feel the problems are easier if you take the time to label what is given. In this case, they're giving us 25.36 grams of oxygen and an excess of hydrogen, and we're being asked to solve for the amount of water that's going to be produced. The fact that hydrogen is in excess simply tells us that we don't have to worry about that in this particular problem. We have all the hydrogen we need. The amount of water that's going to be produced is going to be solely based upon the amount of oxygen. Step 3 is convert given to moles. This is important because it ties in what we did earlier with our molar ratios. A chemical equation is only good for moles. So for every 1 mole of oxygen, we expect to produce 2 moles of water. Well, 25.36 grams cannot be used because it's got to be in terms of moles. So the step 3 tells us that we need to go ahead and convert grams to moles. So I took the 25.36 grams of oxygen, recalling that oxygen is diatomic, so its molar mass is 32, and I now have 0.7925 moles of oxygen. Moles of oxygen is a quantity that we can use in our chemical equation. So now we move on to step 4. Step 4 is going to be what you've already worked on previously in this week. It's the molar ratio. Step 4 is set up a ratio between the given and what's being solved for. We are given the oxygen and we're solving for water. So using our chemical equation, and just like you did last week, we know that for every 0.7925 moles of oxygen that we solve for here, the ratio is 1 to 2. So for every 1 mole of oxygen, I can expect to produce 2 moles of water. And a quick review, remember, if there's no coefficient in front of something that's understood to be a 1. Just like in math class, if you just have x written down, it simply means 1x. So getting back to the ratio, fact table method, 0.7925 moles of oxygen cancel. For every 1 oxygen, we're going to produce 2 moles of water. So our ratio is 1 to 2. I cancel units and do the math, and I see that we can expect to produce 1.585 moles of water, controlled by our sig figs. So we can see that 1.585 moles of water is an actual amount of water, but the question asks for how many grams of water. So now we go to step 5. Step 5 is convert moles to desired units. Now later on, probably next week, we may be converting this to volume or liters, but for the first few days we're working on this, it's always going to be convert to grams. So we're going to convert moles to grams. This is nothing new. We did this previously in the course back in the early spring or late winter. And we simply are going to take 1.58 moles of water and we're going to convert that to grams. The molar mass of water is 18.02 grams. So the answer is 28.56 grams of water. Remember, 18.02 is a given. That does not control our sig figs. The 1.585 moles is going to control our sig figs because that was based on the given mass of water. I'm sorry, the oxygen. So to sum it up, 25 or 28.56 grams of water will be produced when 25.36 grams of oxygen react with an excess of hydrogen. Okay, so a quick review. Step 1, we wrote down a complete balanced equation. Step 2, we labeled what was given, 25.36 grams of oxygen, excess of hydrogen, and what we were solving for. And we're looking for the grams of water. Step 3, we converted given to moles because grams cannot be used with the chemical equation. The chemical equation is only good for moles. So we've got to convert the 25.36 grams to moles. Step 4, we're going to set up a ratio. We want to figure out how many moles of water can be produced based on the available oxygen. So that's where our molar ratio came into place. So we had the 0.7925 moles of oxygen solved for up here in step 3. Ratios 1 to 2. We have 1.58 moles of water that are going to be produced. The question asks for us to solve for how many grams of water. So we simply are going to take the 1.58 moles of water, using its molar mass of 18.0, we convert to grams. And it's just that easy. I want to point out that it's also possible to do a stoichiometry problem in one complete process involving all 5 steps. As you can see, I have the same problem that we had on the previous example. It's the same example. How many grams of water can be produced from 25.36 grams of oxygen? Here's my balanced equation. That's step 1. Step 2, I labeled what I was given. I labeled what I'm looking for. Then down here you can see I've worked it out as one complete step. I took grams, converted to moles. That was step 3 in our 5-step process. I then set up the ratio 1 to 2 between the oxygen and water. That's step 4, setting up our molar ratio. And step 5 was convert moles to grams, which I did right here. So we're doing the same exact thing, except here I'm showing it all in one complete step. This is acceptable too if you would like. If you solve it this way and the question asks how many moles of oxygen are available, you just have to do the calculation here and stop and take your answer. If it says how many moles of water would be produced, you would have to take this, divide by 32, times by 2 and stop, and that'll tell you how many moles of water you have. And finally, if it says how many grams of water, you would then figure out the final problem. It is acceptable to type all of the numbers into the calculator and wait until the end to round the answer to the proper number of significant figures. In this case, 4 sig figs based on the 25.36 grams of oxygen. So it's a matter of personal preference. You can do it one step at a time, or you can solve it as one complete process. Let's go ahead and try one more problem. Here's a second problem I thought we could do together. How many grams of cesium phosphate are needed to completely react with 23.8 grams of magnesium? So we have to analyze this, and the first thing we have to do is come up with a chemical equation. So I have cesium phosphate reacting with magnesium. This is a single replacement reaction. So you have to apply the knowledge you obtained previously in chapter 11, and you need to write a complete balanced equation. So step 1, there's my complete balanced equation. 3 magnesium, single displacement, magnesium replace cesium. We form magnesium phosphate, cesium, checked all my charges. That is the correct balanced equation. Step 2, I suggest that you label the given. In this case, we're given 0.2389 grams of magnesium, and they're asking us to solve for how many grams of cesium phosphate are going to be produced or needed to react, not produced, needed to react. So we go ahead and label the given, and we're going to label what was given. So I was given 23.89 grams of magnesium. They don't know how much cesium phosphate we need to react. Now, these are both on the same side of the equation, but that's okay. It doesn't matter because these ratios go all the way up and down the whole equation. For every 3 magnesiums, I need 2 cesium phosphates to produce 1 magnesium phosphate and 6 cesiums. The fact that both of these are on the reactant side is perfectly okay. We know that for every 3 moles of magnesium, we're going to need 2 moles of cesium phosphate. So the 23.89 grams can't be used. We have to convert to something that's useful for us. So that's why step 3 again is we're going to convert grams to moles. So I take 23.89 grams of magnesium, use the molar mass of magnesium is 24.31, and we have 0.9827 moles of magnesium reacting. So now we have magnesium expressed in a quantity that is able to be used in a balanced equation. Recall, 3 moles of magnesium, I need 2 moles of cesium phosphate. So step 4 is we're going to set up that molar ratio that we worked on last week. So I'm going to take the 0.9827 moles of magnesium, and I'm going to write that down, start with the 0.9287 moles here. I'm going to use a factor label method. I want moles of magnesium to cancel. So for every 3 magnesiums, I put that at the bottom, so magnesium cancels. I want to know how much cesium phosphate we need. So the ratio is 3 to 2, so I write that accordingly in my factor label method. So for every 3 moles of magnesium, we need 2 moles of cesium phosphate. Units of magnesium cancel. I have 0.6551 moles of cesium phosphate. So that is the amount of cesium phosphate required to react with 0.9827 moles of magnesium. The last step, which again is nothing new, we worked on this for quite a bit previously in the year, we need to convert this to grams. So you're going to have to calculate the molar mass of cesium phosphate, which when I calculate, I came up with 493.70. I convert moles of cesium phosphate to grams. I get an answer of 323.4 grams of cesium phosphate. That is our final answer. So 323.4 grams of cesium phosphate are required to react with 28.39 grams of magnesium. As with the previous problem where we had hydrogen react with oxygen to produce water, I wanted to show you that this problem as well can be worked out where we combine steps 3, 4, and 5 into one process. So here's the problem, just like we worked out. How many grams of cesium phosphate are needed to completely react with 23.89 grams of magnesium? So we still have to write a complete balanced equation, and I really advise you to get in the habit of labeling what is given and what you're looking for, which I identified as step 2. We can then combine steps 3, 4, and 5 into one continuous process. We can take 23.89 grams and convert grams to moles. That's step 3. Step 4 is to set up your molar ratio. So again, from the equation, for every 3 moles of magnesium, we need 2 moles of cesium phosphate. So that ratio is shown here as step 4. And then step 5 was convert moles to desired units, in this case, grams. And the molar mass of cesium phosphate was 493.70. So we get an answer of 323.4 grams of water. The units all cancel out, so I know I have it set up correctly. As I mentioned previously, it is acceptable to type all the numbers in the calculator and wait until the end to round the answer to the proper number of significant digits. In this case, 4 sig figs based on the 23.89 grams of. And that's how you complete a stoichiometry problem. If you have any problems, you can contact me during my office hours, or you can get a hold of me through my email. So I have posted 2 Google Forms in Google Classroom and 1 Google Sheet to help you master this content. Again, if you have any questions, don't hesitate to contact me through Google Classroom, through my office hours, Google Hangout, or my email. All right, take care, and I'll see you all soon.